Hi, welcome to the Hidden Gems in NX Manufacturing. I'm Alexander Freund from Siemens Digital Industries Software. This session will be hosted by Vincent and Collin Kopecky from Swoosh. They'll be covering some tips and tricks in NX that can help improve your programming process. After that, it will be followed by a session about managing CAM and CAD data in NX. Both John and Collin will be in the chat to help answer any questions about their presentation. Enjoy!
I'm going to show you a new feature available in NX 1953 called Assembly Load Options for CAM. And now starting with NX 1899, our assembly load options, here if I go and show that, the default option for our load scope option is set to minimally load lightweight display. And what that allows NX to do is load a lightweight display of our assemblies. And this will decrease the time it takes to load assemblies. I'm going to go ahead and load this one right now. And in this case, we have a machine tool loaded in our environment. And typically when I'm working in manufacturing, I don't like to have lightweight components. So, however, from CAD side and working with larger assemblies, I do like to have them a lot of times. So this new feature lets us have kind of the best of both worlds. And so with these settings out of the box, I just want to show this default behavior here. If I go ahead and expand my machine tool, and if we can see, actually it doesn't look too bad here. A lot of times you'll get a very faceted approach, and you can see that it is faceted to a certain degree. If I right click on any given component, you can see that my this option show exact. And essentially what that's meaning is if I click this, it's going to show the kind of the full weight model. And I can click that right now. And NX is going to go think. It's going to fully load that model. And it just becomes a little bit cleaner, crisper picture here. If I don't want to change my assembly load options permanently to handle scenarios like this, we have a new option available in our customer defaults that under manufacturing general, we can specify to always fully load our assembly. Now this is from the manufacturing application, so this is any assemblies that are going to be opened by the manufacturing application. So let's just point this out. I'll go ahead and hit OK. I need to close this session of NX and launch a new one to show the results. But all that's going to happen is, when I go and look and open up my part file, even though my assembly load options are going to be set to minimally load, let's go look at that still. Assembly load options, yep, minimally load. And I open up this same assembly. Once the whole part file opens here, I'll be able to go and see that the machine tool, we looked at that Z-axis component before, we'll see that that is fully loaded now, not a lightweight version. So you might notice it does take a little bit longer to load because we're fully loading this whole assembly now. But again, if I go to my assembly navigator, expand this machine tool, and again come down to this Z-axis, we can see that the option for show exact is gone, and now the option to show lightweight is available. So you can do this interactively in your part file, and maybe let me change my rendering style here. So you can see we have nice fillets and kind of a pretty good appearance on our model. But I can at any point go back to my lightweight version, and this is where, as you're zooming in and out, you might start to see some faceted surfaces. So just a little tip out there that you may want to leave that option turned on. I prefer to have it turned on, and that way if I like to work with any of the minimally load or any of the lightweight versions for my load options, this will fully load all of your manufacturing components.
In this Hidden Gem segment, I will be demonstrating how to create and utilize a fixture reuse library. The reuse library will allow you to store all your fixture models in a central location, either locally on your PC or on the network for everyone to use. Once the library is created, adding fixtures to your manufacturing part file are simple as dragging and dropping. Let's begin. Here I have a machine template with our part already loaded. You can see it's blank. There's no way to fixture our part. I'll add fixtures using the reuse library. First, we're going to want to verify that the reuse library tab is turned on. We'll do that by mouse button 3 on the resource tab, the resource bar, and just verify resource library is checked on. We'll switch to that tab. And here you can already see there's some folders already created out of the box. If we go into one of these, you can see that once you open a folder, you can see what's in there. If you click on it, there's a preview window to show you that it's a hex bolt, some other stuff, a nut. We'll add our own folder for all of our fixtures. To do that, we'll mouse button 3 in an open area, and we'll do library management. You can see that this folder structure matches what's in the library already. And we can add a new library. And we'll browse the location that your fixture folder is stored. Mine is on the desktop. Yours can be anywhere locally on your PC or on a network. You can browse to that location. And you're going to want to go to the upper level of the folder. So mine is named fixtures, and inside is there's 4 folders from different manufacturers. You can click OK. While we're in here, you can see there's this applications pull down. The reuse library can be accessed from any NX application. This can be modeling, drafting, and so on. If you highlight your folder and do applications tasks, you can turn this specific folder on in any of these applications. Let's add modeling, for example. So if I were to switch to the modeling module and go to the library management, you can see our fixture reuse library is there as well. I'll switch back to the manufacturing module, and I'll start pulling in some models and assembling this part. You can see once you open a folder, there'll be a small graphic. You'll have to save each component for that thumbnail to save. For example, I did that with some of this, so you can see each component has its own thumbnail. So all you have to do is hold mouse button 1 and drag into the open window. And it comes in on a different layer. So I'll switch that layer on. So I brought in a Shunk quick change palette. And now I'll bring in a multi-clamping vise. I'm just pulling everything in, and then I can assemble it after the fact. Do our center jaw. And 2 movable jaws. And we can begin assembling. I'm just gonna reposition everything so it's easier to work with. Just center this on our T-slot table. And we'll give it a distance off the edge of the the table. And we'll assemble our vise to the quick change. One thing I like to do is use a distance when aligning my vise. That way I can, once everything's assembled, I can easily switch positions if there's any clearance issues. And continue, I'll do the center vise. And our jaws, our vise, and our quick change table are assembled. We can do our part now. And we'll assemble our movable jaw to the part. And yeah, within a matter of minutes, you have your work holding assembled to get a full digital twin of the real world.
In this segment, we're going to look at a new function for easily placing a WCS on a block or a part boundary. So here we are. I have a sample part, a couple of vices on a tombstone on a 4-axis horizontal here. And if I go to my geometry view, you can see I have 8 workpieces for the 8 pieces of material I have here, as well as an MCS inside of each workpiece. And in this case, I always wanted my my MCS to be located at the center of my block. So in the past, I'm going to show how I would have done it on this part on the lower right-hand side. Currently, I didn't create any blank geometry, so let's do that first. I'll go ahead and edit my workpiece and specify this part. And I'm going to use the option bounding block. Now these are requirements. You have to use bounding block, bounding cylinder to have this functionality work. Because it's actually looking at the bounding body, and I'll show you here what gets created in a moment. Let me just enter in the size of this block. Alright, so we have our blank geometry created here. And you can see now in 1953, we have the option of creating our blank geometry as a body inside of our part navigator or as a separate component. I'm going to leave it as body. Alright, so now we can see that geometry was created. And before we go into specifying a work coordinate system here, or sorry, a machine coordinate system here, let's just take a look at our part navigator, and we can see what was created. Inside here we have a feature group for my CAM workpiece 8. This was just created when I created the blank geometry, And there's two bounding body features in here. One is the blank. When I created it, I had an option checked to display my blank geometry. So that's why it left this bounding body displayed. But it also creates a bounding body around your part without any offsets. So I can always display that. And I don't know, it might be a little bit difficult to see here. Maybe I'll try changing the colors real quick. All right, so now you can see you have a bounding body of your part and of your block. All right, so in the past, before this feature, there's a lot of times, simple scenario here, you just want to place your MCS at the center of your block. So my typical workflow would be I would go ahead and edit my MCS. I would launch the CSys dialog. Here we have dynamic active. I would activate the point dialog from the manipulator and come down and choose between 2 points and pick, opposite corners or midpoints or something like that. Let's just do opposite corners in this case. And of course, you see we get our MCS created, as you would probably expect. But of course, we went through a number of dialogues here, maybe more than you would have wanted to do. So let me just go ahead and cancel this, and I'll show you the new method here. So long as you go ahead and create blank geometry, like we did here, once you do that, you get this new option available, origin location. And from here, specify would be our kind of default behavior. But now we can specify a point on the blank. So this is going to be on my blank box here, which is kind of this pinkish red color. Or I can specify it on my part box, which would be the green box. So in this case, let's choose on blank. It's going to automatically grab workpiece 8 because that's the parent object here. And now in this view, I can just go ahead and pick different points, whether I want the center point, corner of faces, and you'll see in my graphic window that display is being updated at the same time. So I can just simply pick that part or that point, and the MCS is created at that location. And of course, I can go through and move it to different locations depending on what would be needed. Likewise, if I didn't want to specify the MCS on the blank geometry, I could specify it on the part box and do the same thing. And let's pick a corner here. You can see that, yep, it's picking the corner of my part box. So if I wanted to just touch off of essentially 2 corners, if I had some whip here, that I had some finished surfaces that I wanted to touch off, I could quite easily specify that geometry as well. And like you would expect or existed in all the previous versions, the details here about how you specify local, fixture offset, that type of information is all the same. Okay, so that's how the kind of that easy set works here for the MCS. But I just want to take a step back and point out, here we have the origin location. Had I not specified my blank geometry, in this case, let me just go ahead and set this to geometry instead of using the bounding blank. Yep, this is telling me that since I changed it, the blank geometry will be deleted. Do I want to do that? And yes, I do. All right, so now you no longer see that blank geometry. If I jump back into my part navigator, my feature group is gone. I have feature groups for all the other parts, just not this 8th part. So now if I was going to edit my MCS, you'll note that that origin location option is not available. So this is a thing that I just wanted to point out and make sure people are aware of, that you have to specify that blank geometry before setting the MCS. Otherwise, you won't see the available option here to set to on part or on blank. All right, I hope that's going to be beneficial for you in scenarios where you have to set up multiple work pieces and you're setting up many MCSs. I think that'll be a time saver. Thank you.
In this Hidden Gem segment, I'll demonstrate how to add a manufacturer's holder model to a tooling assembly. Solid model tools are important for accurate simulation. Tool models, along with machine and fixture models, will ensure the program you create within NX will be a true digital twin of the program at the machine. Having an accurate assembly in NX will save time and money with unneeded program changes or costly collisions. Let's begin. Here I have a blank manufacturing part file open. This can be either done in modeling or manufacturing. I'm going to show this in manufacturing. I'm going to start by importing my solid model. So it's file import step 214. And I got this model from Machining Cloud, so I built the assembly within their web-based application. So all three components are assembled. If you have components individually, you'll need to assemble those within NX. So the model's in my workspace. We'll need to position this so it's in line with the x-axis. I'm going to go to the assembly navigator and highlight my three components and mouse button 3 and move. I'm going to move my move handles to the portion where it's going to engage with the spindle. So I'll check move handles only, and I will select the origin. And move it to 0, 0, 0 within the model. Now I'll uncheck the move handles only so I can move the model, and I will rotate this 90 degrees. So now we're in line with the x-axis. Our tooltip is going to need to be on the ZY plane. So I'll move this 3.75. That's the gauge length of the assembled tool. And okay. Now we have our model positioned correctly. And so we can begin to create the cutting item. So I'll insert a new tool. With NX, you need to describe face mills as mills. So this is going to be a flat bottom tool. So having a 3D model is important for an indexable tool that you would ramp with or helical interpolate. You probably typically won't do any ramping or helical interpolation with this tool. So I'll name this face mill. You can see that the tool is not positioned in line with the assembly. We can move that so it's easier to see what we're doing. Again, 90 degrees. And just pull up. So this is a 2-inch tool. It has a taper angle of 45, a length of 0.276 and a flute length of 0.276. So that will create our cutting insert. And we can give this a description, face mill. And it is 5 flutes. From there, we'll go into our holders tab and we'll give this a description and a library reference. This can be anything you want. I'm just going to name it face mill. We're not going to do anything within the holder portion. Once we export the tool from here, the holder will be saved and the cutting information will be saved. We'll give this a library reference for the cutting item, just generic name, face mill, and we'll check the export tool part file, and that'll bring up some extra dialogue. We'll need to define the mounting junction. This is where the tool meets the spindle. So we will put that right at that point. And the tooltip is the tip of the tool. This is already defined because we positioned it in this position. And then the next thing is we'll need to select our cutting inserts. And we can click Export Tool to Library. And under Target Class, this is a nmil indexable. And this holder system is not important. We can click OK. And I have a file already set up. We'll import our tool that we just created. And we'll retrieve this from library. We'll search by class so we don't get so many results. So it's milling, nmil indexable. And I created that tool. It was an inch tool. This template file is in metric. It'll still work. It'll convert all dimensions over. So we'll switch the library units to inch and hit OK. And we have our face mill created right here. You can hit display and it'll show the tool. All right. Cancel. I have an operation already created. And we'll generate. And we can verify this toolpath. So we're under 3D Dynamic. Under this tool display, we have this set to tool. So all you're seeing right now is the insert. So there's really no collision detection with this method unless you go into machine simulation. Right now, this is purely visual. So we'll switch to the assembly, and you can see you have the tool we just created. And if we go ahead and hit play, I have a UDE set, or UGII environment variable set to have the tool spin. A little extra hidden gem. If you go into your UGII env.dat, and you can set this UGII _enable _cutter _spin equals 1. That will allow the tool to spin. I mentioned that the solid tool model will only be used for collision detection in simulation. This is because the holder was not described on the holder tab. I wanted to show off the results of a feature enhancement in the next release of NX 1980. The holder import enhancement will create a revolve based off of the solid model and automatically create all the data sets necessary to describe the tool holder. I've already went ahead and added the tool with the solid model and holder. If we click on it to see the preview, you can see there is a solid model attached. If we open the tool and go under the holder tab, we can see there are all these data sets that are there, and that's describing the outline from the tip of the tool holder to where the holder meets the spindle. You can certainly do this manually. You'll have to measure each point. You don't have to get as detailed. This is going to follow this whole profile, including this flange part here. It's not typically needed when you're simulating or looking for collision detections. You're not going to get that close to this cutout anyway. If we verify this toolpath, this is the finished model you're going to get from all those data sets. If we switch to assembly, you can see the solid model is still there. If you were to simulate right now using the assembly and there was a collision, it will look at this holder data and give you a warning. In conclusion, adding solid tool holder models in conjunction with fixture and machine models will ensure a reliable and accurate digital twin of your real-world machine setup.
Okay, here we are looking at a 4-axis machine tool and a part that I have programmed. And a common issue that I see being encountered will come anytime you're trying to do like 4+1, or sorry, I should say 3+1 operations. We're trying to do some rotary motion with your on a 4-axis machine. Deburring is a great example where the machine tool will actually cause a gouge that's not shown in your tool path here. And I just wanted to go through and show how to work around this and give an understanding of what is causing this. So first I'm going to go ahead and simulate this chamfering operation just so we can see. Hide my operations here just so we can see this happening, and I'll play this a couple times. I'll play it through the first time, and then the second time I'll step through and we can look at the machine code all at the same time. So you can see right away I'm getting a collision found. Let me zoom in here, move this error message out of the way, and I'll say continue, and we can see that we are indeed gouging our part. You can see that gouge left behind. You can see the tool is pretty deep into the part. Definitely not something that you would want to have happen as you're running your part. But again, if we display our tool axis here, or our tool motions as we're coming up to this next corner, you'll see that this motion certainly does not represent what we saw in inside the actual operation. And okay, I'm going to go ahead and reset this, and we'll take a look at why this is the case. I'm just going to scroll down in my code here a little bit, and here we'll see the first couple A motions as we're going to start rotating our table. So again, we're bringing the tool down, cutting across. I'll just let this play again through the to the next corner here, where we can take a better look at some of the code and various motions. So right here, we're stopping. I just put a stop point break in the program here. So in the program, we're simply moving to the next linear position and a position. But on a 4-axis machine, typically we don't have any type of tool center point control or kind of 5-axis mode to control synchronizing of the linear axes and the rotary axes. So we can see when we try to make this motion, all the axes are trying to just get there as soon as possible. So in doing so, we're going to be resulted with this gouge. The motions are not synced and staying relational to each other, and that's what's causing this gouge motion. So one option, of course, is to look at adding an option for tool center point control to your machine. But a lot of times, if this is your typical parts prismatic shapes here, it's really kind of overkill for the scenario. So I'm going to just finish this simulation right now. And if I go ahead and look in my operation here, all I'm going to do is I'm going to add a user-defined event. And if I come down, I'm going to use this user-defined event. And let me make my window a little bit bigger here. And I'm going to add a command to set linear tolerance. In this case, I'm just going to set linear tolerance, lintol, equal to 1/1000th of an inch. And I'll say OK. So nothing really happened in my toolpath. No, I didn't change the toolpath whatsoever. The motions inside of NX are exactly the same. But what I changed by setting that linear tolerance is how the post-processor is going to interpret the motions and the various events it finds. And it's actually going to linearize the motions when A is moving here into smaller segments. So I'm just going to post the code first here. And if you remember looking at the code where I stopped it and we kind of looked at the A motions in the first segment there was only, I think, 3 A motions. Now for each motion, here we are previously at A270, and instead of in one line going directly to A225, we're doing a series of smaller motions. And that's going to allow the machine to kind of just walk through that tool path without having any calculations being done by the control. So you can see I have a series of different A motions anytime we're making some big changes here. So let's go ahead and run the simulation again and see what this would look like on the machine tool. Alright, here we go. Let's see, now we're coming down positioning. If you notice, already we were encountering gouges prior to adding this user-defined event. And now we're just repositioning. Oh, I still have my stop in here. Let's delete that breakpoint and continue on. And through all these motions now, you can see the machine is interpreting all of those linear segments as opposed to just one big motion. And this will allow you for these types of operations to get the output that you want. Typically in a 4-axis machine, you always have to have your tool axis normal or kind of away from the center line of the rotary to avoid these types of motions. Well, in chamfering, we want our tool to be normal to our part surface so that's not going to work for us. And that's why we have to kind of go through this method of modifying how the post is interpreting our tool paths. And again, if we zoom in and look, you can see, yep, in fact, our IPW is chamfered without any gouge motions now. Let's bring this back around. And maybe I'll reset this and we'll just take one final look at it. We slow it down and come in. We're chamfering this first corner, making some A motions right away. So you can see just interpreting all those individual linear segments. If you use this method and you notice that the motions or the surfaces where the A is moving appear a little faceted, you can just play with the tolerance value that you're setting in that lintol user-defined event. The smaller you make it, the more segments are going to be broken apart and the smoother the resulting surface will be. So all users out there use 4-axis machines without any TCPC type control functionality. Give this a try next time.